Okay, so let me tell you about the free response. I told you in class today. Let me just reiterate, and I have something else I want to add to that. Can I turn the lights down up here? There's a glare on the screen. Okay, so as I told you in class, I'll give you a configuration of charges. It won't necessarily be like that. Like they can be like that or they can be like that. But the point is that I'll ask you for the electric field at a point where the field vectors are one is on axis, one is off axis. We can work through one of those later if you like. I'm going to ask you a variety of things. Like I might ask you to draw the force vectors like this, in which case I want you to also label the angles. In this case, it would be to label this angle. I'll tell you that on the exam. So like that would be a part. Calculating the magnitudes, E1 and E2 might be a part. That's just going to be, KQ over R squared. And then calculating, this is E1, and if this is E2, calculating the X and Y components might be a part. So that would be, for example, E1X and E2X. That would be, E1 cosine theta, E2 sine theta. And then once you get that, finding the magnitude and the direction of E. So finding E and the direction, the magnitude, E, and the direction. We can do that. That's where you take the X and Y components of the final vector and use the Pythagorean theorem to find that resultant, and then use your inverse tan to find the direction of that vector. Then also, I'm going to ask you, what if I put a particle here that has a certain charge, say, I don't know, Q equals 2 coulombs. What is the force that acts on that particle? You can find the force for a particle in an electric field just by multiplying it times the electric field. Once you have the electric field, it's simple. You just multiply it by the charge to find the force. I think that was it. Oh, no, that was a different problem. So that's all one problem. It's actually like 5 parts to it, though, so it counts as 5 separate problems. Remember to show your work. I'll say that in the problem. You won't get credit unless you show your work. You just write a number there. Even if it's the right number, no credit at all. You have to show your work. I'll say that on the exam, and I'll say it again on Monday. Show your work. And then if you get the answer wrong, but your work is mostly correct, then I'll give you half credit. Okay? So it's a win. Well, it's a win, partially win, lose situation. But you want to at least be in the partially win or win category. There will be another question. We worked through some of these earlier where a charge moves through a change in potential, and I ask you, what is the speed of that particle? Okay? Remember, voltage is energy per charge. And so if I want the energy, it will be the voltage times the charge, or rather the change in potential times the charge. So that would be 1/2 mv squared equals v times q. And then I can solve for v. We did a problem like that, but we can do another one today if y'all want. And then finally, I didn't tell you all this in class today, but I'm saying it now, is that you're going to have to draw electric field lines like you did in lab. It's going to be a dipole, 2 charges. They may be not the same, so it might be, I don't know, +2, -3 or something like that, in which case you would have to, gosh, how would that go? Well, the simplest way is just to draw 2 field lines like that, although I actually say, I tell you to draw 5 to 6. Ooh, I'm going to have to fix that. 2 field lines like that, and then I would have a 3rd field line like this, right? Because that's a bigger charge, it's going to have more field lines. You could draw a couple more, if you like, but then I'd have to draw another one like that. Okay, and then I'm also going to ask you to draw the equal potential lines. Equal potential lines, remember, are always perpendicular to the field lines. like that. Those are equal potential lines. Just like you did in lab, not a complicated structure, just two charges, but two dissimilar charges, two that are different. Okay, those are the first 8 questions on the exam. That's more than a third of the exam, or almost a third.
Are you going to like positive and negative, or like you have to know if there's 2 charges that are both positive?
They'll be different. I don't know I don't remember if I did it 2 positives, 2 negatives, positive and negative. If it was +2 -3, this is how it would look. You would have field lines going out like that, +2 +3 rather, and then like that. I do 4 here. If I do 4 here, I have to do 6 here. Okay? But it won't be 2, 3. It'll be something else. I don't remember what it was. I'm pretty sure it was a +-, but it might not have been. You should know how to do either. The field lines, by the way, will look like this. There will be no field lines in the middle. There's no equal potential lines in the middle. The equal potential lines will look like that. Okay? That's easy, right? The first 8 questions, I can do all that, I think, just with a little bit of work over the weekend if you're a little shaky on some of it. What would you like to look at first?
For spring 16, number 17.
Okay. That's the one exam I didn't bring. Let me pull it up online. Spring 16, number 17?
Yes, sir.
Make sure this works here. Yeah. All right. Okay. So what is the charge that can be stored on this capacitor? So you're going to have to do this for a capacitor. You're going to have to calculate the capacitance of a capacitor. And remember, the capacitance of a capacitor is kappa. I'll write that up here. Kappa epsilon naught A over D. So the kappa is the dielectric constant. That's 3.7. Epsilon naught, that's on your equation sheet. I'm not going to give it to you on your exam, but it's on your equation sheet. That's 8.85 times 10 to the minus 12. A is 0.04 times 0.05. I'll probably give you the area, but here I gave the dimensions. Divided by the distance between them, that's 1 times 10 to the minus 3. And so if I do that, I calculate my my capacitance. Oh, low battery. 3.7 times I get 6.5 times 10 to the minus 11. But this is that's in farads. This is asking how much charge can be stored on a 1.5 volt battery. So remember, Q is equal to C times V. So it's that times 1.5. I get 9.8 times 10 to the minus 11. So E is the right answer. 2 steps on this, and you need to know how to do both of them. Calculate the capacitance given the dimensions of a capacitor. You have the equation. You just need to know what all those values are. And then also use this to find the charge on a capacitor. Definitely going to have that, both of those on the exam.
Where'd you get 8.85 times 10 to the negative 12 from?
Let me show you. So on the equation sheet, I actually put your equation sheet, I don't give you the whole thing. I put it on the last page of the exam. There was a blank half column there, so I put our chapter 1 and 2 equations on that. It's all those constants are right here. So that's our epsilon, our permeativity of free space. Okay, notice also that the fundamental unit of charge, that's the charge for a proton and an electron. And then I also have the mass of the electrons and protons here. Those are the things that you're going to need. Of course, you'll need K as well, but I think most of you've used K enough that you know it. Okay? All right, what other ones, particular questions you have?
I think it's
Yeah?
number 7C.
Remember, on this exam?
Yes, sir.
I don't know what the answer is. Let's see, number 7. It's C, right? Are y'all feel comfortable with the 2D vectors, or do you want to go through that? Okay, let's go through that. Haven't done a whole lot of free response on exams, but I guarantee you, I know you're a little nervous. Are you nervous about free response on your exam?
Yes.
Yeah. But people tend to do better. My grades tend to go up when I have free response because you know what the questions are. I'm pretty upfront about what they are, and like I said, the whole partial credit. So don't be nervous. This is a great example of what you're going to see on Monday. This whole page, except I don't have drawing the field lines on this. So the first question is, what is the magnitude and direction of the electric field at point A? Measure the angle from the x-axis. And as I said, I would actually have 1, 2, and 3 all in one question. I do have it all in one question. I don't have them spread out. And then there are a couple of subparts as well, like calculate AX and AY or EX and EY, which you have to do anyway en route to the answer, but I just make it a separate question. So I want to know the electric field at point A. I imagine there's a positive test charge there. And I ask myself, what is the direction of the force due to these other 2 charges? Q2 has a force that's up and in that direction because it's an attractive force. That's also the electric field. And then Q1 has a force in that direction. So this is E2 and this is E1. The electric fields are in the same direction as the force that that positive particle would feel. A couple things we need to do. The first thing is let's just recognize where our coordinate system is. This is our coordinate system. And I need to draw this angle. E2, that's 3, 4, 5 triangle. So I know that this angle is 53 degrees. But if you don't just know that, this is a 3, 4, 5. I want to know this angle. Theta is the inverse tan of 4/3. And that's 53 degrees. Okay, so if you don't know that triangle, it's just, I like to use it because it's not a trig class. If you know the angles, that's great. It saves you a little time. Okay, it will be a 3, 4, 5 triangle on your exam. So now the next step, and by the way, when you're working on this, there's not unlimited space on the paper, so I recommend that you sort of apportion your space as you go along. You can use your bubble form if you need extra space. There's that block on your bubble form. If you run out of space, then you can go over onto that. And if you need space, just ask me. I can give you a scratch sheet of paper, but I'd rather get it all on this sheet of paper. Yeah. Oh, no. No, you want to measure your angle from the x-axis because you're going to use that angle to measure the x and y components. And so the angle always needs to be for the vector that's off-axis from the x-axis, whichever one is closer, either the positive or the negative x-axis. Always that angle. Or, like I said, if the vector is in this direction, you're going to be measuring this angle. Okay? Are you sure? Okay. Okay. All right. Next step is we want to calculate E1 and E2. I'm going to try to make the numbers really easy, okay? I think I did that here. It's KQ over R squared. So E1 is 9 times 10 to the 9th. This is my Q1, so 9 times 10 to the minus 9 divided by R. This distance is 3, so it's 3 squared That cancels, 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 cancels. It leaves me 9 newtons per coulomb. And then E2 is very similar. 9 times 10 to the 9th. 25 times 10 to the minus 9. No negative sign there. It's vector quantity. Divided by 5 squared. Cancels, 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 cancels. That leaves me 9 newtons per coulomb. So now I have the vectors E1 and E2. The next step is to find E2x and E2y. And this would be a separate problem in the problem, like a subpart that would count the same as one of your multiple choice problems. E2x is E2 cosine theta. E2y is E2 sine of theta. That's going to be 9 cosine 53, 9 sine of 53. That's how we find our x and y components. Remember, cosine is always the x component when your angle is measured from the x-axis, and sine is always your y component. So I have 9 cosine of 53. That's 5.4. 9 sine of 53. That's 7.2. All right, so those are my two components of E2. If you want, at this point, you can redraw your coordinate system. I like to do it. You don't have to, but I find that it helps me to think about my vectors and then draw those vectors on here. So I have E1, which is in this direction. That's 9 newtons per coulomb. And then I have E2x. E2x is going to be in this direction. So E2x is 7.2. And then, excuse me, not 7.2, 5.4. And then E2y is going to be in this direction. So that's going to be 7.2. Now, notice why I drew the x and y components on those axes. The reason I did that is because E2 is right here. Its y component is going to be on the positive y-axis. Because E2 is in the second quadrant, the projection of E2 onto the y-axis is not on the negative y-axis. That's way on the other side. It's on the positive y-axis. But the projection onto the x-axis is onto the negative x-axis. It's like a shadow. Where does that vector cast its shadow? Or where does it project onto? Okay, so now that I have that, I can figure out my EX and EY. Notice I don't have a subscript number on these. These are the x and y components of my final vector. EX is going to be 9 minus 5.4. That's what? 3.6. EY is going to be 7.2. And then finally, to find E, 3.6 squared plus 7.2 squared. And then to find the angle for E, I'll call it theta, is going to be the inverse tan of opposite over adjacent. That's 7.2 over 3.6. And then that'll be whatever it is. So those are my answers. But with one caveat, let's be careful that we understand where this vector is. That's where drawing the pictures becomes a lot of help for you. I have my components 7.2 right here, and 3.6 is in the positive x direction. Remember, 3.6 was this component. The reason it's positive is because 9 is bigger than 5.4. So it's 9 minus 5.4. That gives me positive 3.6. That means that my final vector, E, is going to be in this direction, and this angle is the angle that we calculate right here. So I'll ask you to measure that angle from the positive x-axis. And in this case, this would be whatever this angle is. Let's see, 7.2 or 3, inverse tan of 2. That's 63 degrees from the positive x-axis. But recognize that if it was over here, you would do that a little bit differently. If my final vector was over there, I would calculate this angle, and then I would subtract that from 180, because really I'm looking for this angle. We've done that a bunch of times, So make sure that you can do it on Monday. Lex?
So everything macro, if we put whatever the angle is from the minus x.
I asked explicitly for it from the positive x. So yeah, but I do ask explicitly for it. You would get a half credit for that. All right. Anything that's not the right answer doesn't get full credit. I have to have exactly the right number. You know, if you round a little bit differently, I'm not going to count for that. But if it's something like that, even if it seems small, you'll just get half credit. Okay. All right. Tammy.
I would say then like why you put the 9 on the right, why 5 and 4 on the left.
Yeah. So the 9. Why did I put the 9? E2. Okay, so this 9 right here is E1. That's what you're asking, right? And remember up here when we drew E1, E1 is in the positive x direction.
Oh, okay.
Yeah, and so the 7 or the 5.4 is E2x. So this is E2x. And the reason that's in the negative direction is because this vector is in the second quadrant. So its projection, its x component, is in the negative x direction.
I would have it wrong.
Okay. Yeah, I know, it's all a jumble of numbers at some point, isn't it? But it won't be. Like, you'll have this down cold by the time Monday rolls around. Right? Good. That's the right answer. Okay. There are some other things here that you have to do. What is the potential at point A? I think this is pretty straightforward. If you've done this a couple of times, I think that it's not terribly complicated. So remember, this is the sum of the potentials, KQ1 over R1 plus KQ2 over R2. So that's 9 times 10 to the 9th. Q1 is 9 times 10 to the minus 9, divided by R1, which is 3, plus 9 times 10 to the 9th, negative 25 times 10 to the minus 9, scalar quantity, so you include the signs, divided by R2, which is 5 meters, and then we get some cancellations. And then whatever this is, it's equal to 27 minus 45 minus 18 volts. Okay. That'll be all part of the very first problem. There'll just be all those jumbled up together, and then I give you lots of paper, and you can just go through and do each part. I don't spread them out like this. Okay? Make sure that you label them properly so I can see them. And I'll say this to the class, but also circle your answers very clearly. It just makes my life a lot easier if they're circled. Okay, and then you want to do number 4 while we're here? Is that okay? You're going to see one like this too. I told y'all that, right? Yes. So I can't read that. What does that say? Oh, 8 volts. A proton moves from a potential of 8 volts to a place where the potential is minus 2 volts. What is the speed of the proton? So first of all, I need to know what delta V is. Delta V is V final minus V initial, minus 2, minus 8, minus 10 volts. One mistake the students will make is they'll say it's 6 volts instead of 10 volts. But in this case, it's minus 10 volts. The sign in this case doesn't matter that much because we're just looking for the speed. Also need to recognize it's a proton. That'll tell me its charge and its mass. So to find the speed, remember, voltage is energy over charge. So if I want to know the energy, which is 1/2 mv squared, I do Q times delta V. And then I solve that for the speed. V is equal to 2Q delta V over M root. So that's the square root of 2. And then remember, get your charge and mass on the equation sheet. 1.6 times 10 to the minus 19. 10. Just going to leave that negative off. I'm just looking for the speed, so it doesn't matter. And then it's a proton, so that's 1.67 times 10 to the minus 27. And then whatever that answer is, that's the answer in meters per second. Okay? As I told y'all, be careful with your calculators, especially when you're doing stuff like this, where you have numbers in scientific notation in the denominator. Your order of operations can get kind of wonky especially if you're using the times 10 with the caret. Use the EE button. That'll make your life a lot easier. Just be careful with that. Make sure you're doing your order of operations correctly. Often students will make a mistake where this number comes up into the numerator because they don't put it in parentheses, and then the answer is wrong. And even a calculation error, you'll still get half credit even if you've done it right up to that point. I know that seems harsh, but on a multiple choice question, you wouldn't get it right at all. So it's actually it's better for you. All right, and then otherwise, like I said, that's the whole first 7 questions, and then the last question is drawing electric field lines. There you go. That's a third of the test, I've told you. Yeah, Bailey? Oh, because, yeah, so why is this not negative 10? Yeah, because I'm looking for the speed, and it doesn't matter if it's a positive or negative 10. It's just, in fact, if you tried to put a negative in there, it would, you couldn't do that, right? It's square root of a negative number. Okay?
So how would that question be worded if we need to use like the other, like the key, delta, like,
The delta.
the other one that you said was like.
Oh, yeah, so we did a different one in class, and you can see this in the multiple choice, but it's not on the free response. It's a different type, it's a similar problem, but it's dealing with electric fields instead. So where I have a charge moving through an electric field over a certain distance, delta x, this is what you're talking about, right? Yeah, so if you look on your equation sheet, where is it? Here it is. The change in energy is QE delta x. This is not complicated. This is just our work is equal to force times distance, where QE is our force. That's from our definition of electric field. Work is, by the work energy theorem, we can equate those, and D I just changed to delta x. So here, if I want to know its velocity, I would say 1/2 mv squared. That's my kinetic energy that it gains as it moves through that electric field, is equal to Q times the electric field times delta x. So you would know because I would give you the electric field instead of the potential. But again, this is still the same problem. Like if I gave you the equal potential lines, then you'd solve it the other way. Like if I knew that this was, what would it be? 12 volts. It'd have to be 10 volts, a lower volt. Like if I gave you the potential difference between those two, you could work it the other way, or use the electric field. Same scenario, but you approach it from 2 different ways. Is that okay?
Yeah.
Okay. All right. Other particular problems, Megan?
But can you draw the electric field lines for 2 negative charges?
Mm-hmm. So first, if I just have 2 like negative charges, it would look just like the 2 positive charges. Oops. Except the field lines terminate in negative charges. If I have 2 charges that are different, then it would be similar. I would just have, in this case, twice as many field lines going into the -2 charge. Okay? I think look just the same. This is the same as for the positive charges, except the arrows are going the opposite way. So for example, if you did this and you got the arrows going the wrong direction, but it was otherwise right, that would be half credit. I try to be pretty liberal with the half credit. If it looks like you know what you're doing, then I tend to give half credit. So if you feel like you know most of what's going on, just write something. Don't dawdle on the free response, okay? Because there are a whole other 20 questions to answer. I'll tell you after about 20 minutes that, hey, if you haven't finished, you might want to move on pretty quickly.
How much time do we get to take the exam?
Well, let's see. What class? Class is what, 50 minutes? 55 minutes. I'll give you an hour. There's another class after us, so we're limited by that class. But I'll give you an hour. That's what I did last year too, last semester. Isn't that right? I gave you an hour? Yeah. Oh, but we were on Respondus last semester. That was for the birds, wasn't it? Okay. All right, what else? Let's look through some of these.
Back to fall 16.
Fall 16? You mean spring 16?
Spring 16.
Mm-hmm. Yeah, what?
22.
All right, what'd you, Lex, what you got to? Mm-hmm. Yeah. The electric potential 1 meter from a certain charged particle is 4 times. So this deals with electric potential. V is KQ over R. And the first particle has 4 times the potential from the second particle. That has 4 times the potential. That means the first particle must have 4 times the charge. So the first particle has 4 times the charge of the second particle. Because the first particle has the bigger potential by a factor of 4, they're both at the same distance, 1 meter, 1 meter. So the only thing that's different is the charge. It must be 4 times the charge of the second particle. Sometimes these are hard to read, huh? But it's good practice for y'all, especially you pre-meds and other, professional folks, because your MCAT and your DAT and all that, it's going to be similarly difficult to read. A lot of those are really about reading comprehension, frankly. Like, how can you read and understand these questions? Okay. Kinematics, is that okay, Luis? All right. Let's see if there's one. Well, we'll look on. I meant to go back and look. I don't remember if I put a kinematics. I don't remember it specifically. There's no freebie question on these exams. I lose that when I go to the 20 multiple choice. Let's see one. Okay, here's this one. We might have done this one today. Did we do this one today? Is that one okay, or you want a different one? I can look. Let me keep looking. Okay, here's another one. Well, this one's a little bit different, but yeah, let's do this one. Because remember, there are 2 ways to find the force. That I can find my force between 2 charges by Coulomb's law, KQQ over R squared. And that's what that previous question was. That's the first step, is to find the force. Or I can find it by the electric field, Q times E, if I have the electric field. In this case, I do have the electric field. I have 1 charge that's in an electric field. And so I have 3 steps. 1, find the force. 2, find the acceleration, and then 3, find the velocity or the displacement. It's going to be the velocity, though, if you have one of these. So the first step is to find the force. The force is equal to Q times E. This is a 4 Coulomb charge with a 50 Newton per Coulomb electric field. So it's 200 newtons. Now these numbers don't make any sense at all. Like that's really a really big electric force. Next, I find the acceleration. That's F over m. That's 200 divided by 5. The mass is given right here. That's 40 meters per second squared. And then the final step is to find the velocity. That's a times t. That's 40 meters per second squared times t. I give it to you right here. Times 2. That's 80 meters per second. So C is the right answer. Okay? Find F, find A, find V. Remember, these are not on the equation sheet. Newton's second law and that kinematics equation. All right. Look, there's an electric field where it's, what's that? Is that positive or negative? 18. Those are positive, right? Because the arrows are coming out. They always come out of positive charges.
What is the answer?
Oh, no, so the electric field is largest where the electric field lines are closer together. So C is actually the smallest electric field. The electric field is biggest right there. You see how these lines are really close together? But here the lines are far apart. Here they're even farther apart. And here they're pretty far apart too. You can also think about this in the terms of how close are you to the charge? Because the closer you are to the bigger charge, the bigger the electric field is going to be. Remember, E is kq over r squared. So if I get really close to r, or if r gets really small, if I get really close to the charge, then E is going to get big. Let me repeat that. So if I have, well, let's just say if I have these two charges right here. My electric fields look like that. If I pick several points, say right here, right here, right here, where would the electric field be biggest? We'll do A, B, C. It's going to be at C. Now notice that this point is really close to this charge, but this is a smaller charge. So here, I'm close to the big charge. My electric field lines also are closer together there. I can tell that. But C is going to be where the electric field is biggest. You understand that? Sure. With the what now? At B? Yeah. Yeah. Because you're closer to that charge. All right.
What about 21?
Oh, which of these is a conservative force? Remember, conservative forces conserve energy. This is in the notes. We haven't talked about this in a while. Conserve energy. Those are all field forces. An electric force is a field force, and a gravitational force is a field force. A frictional force is not a field force. It loses energy. And electric potential is just not a force at all. So it's only 1 and 3. All right.
Like you would give us the charge and then we'll have to like draw the electric field lines, like something like we did earlier, where you gave us like I don't know, the +2 plus the charge.
Right.
And then we do like can we do that? Like if they have to give an example.
Sure. So let's say +4 coulombs and +6 coulombs. Or no, let's do minus. I'll do a positive. plus 4 and minus 6. Easiest way to think about this is I'm going to get 4 lines coming out of the 4 coulomb charge and 6 lines going into the 6 coulomb charge. Like every line represents a coulomb of charge. That's probably the easiest way to start. But then I have to have 2 extra lines. So notice that these do not go into the plus 4 coulomb. And then if I were to draw equal potential lines, the way that I draw those is every time I come up to a field line, that angle should be 90 degrees. They're perpendicular to the field lines. Look like that. You could draw more to fill it in.
So I was gonna ask, like, does it matter the number of
I tell you, yeah, I tell you how many lines to draw. Okay, Megan?
The equal potential lines never go out of the field lines, like it wouldn't be a complete circle, or would it?
Yeah, you could have it where they don't draw it like this, but that's what you did in lab, right? Like you saw it made a circle in lab. You can, if you have a plus Q and a plus Q, like 2 identical charges, which is not what you're going to have on the test. I think, yeah, you can get equal potential lines that go around like this. Yes. Yeah, I guess you get it on these too. That, yeah, these will come back and meet. Yes. So yes, the answer is yes. Never mind. Yes, that's the answer. Yes, that they do come back around. In fact, these will come back around too if you come out far enough. Okay?
like in the base one?
Yeah, it's fine. You don't have to draw it as a circle. But it does. It does come back around. Okay? All right. Anything else, Phil? Oh. Units for what? For everything? Yeah. So, oh gosh, what do we have? I mean, force is in newtons. Electric field is in newtons per coulomb or volts per meter. And then if I want to do this in basic SI units, it would be kilogram meters per second squared coulomb. Yeah, that would be it. Voltage is in joules per coulomb. That's energy per charge. Potential energy, of course, is joules. I think that's everything. Let me look at the equation sheet. Capacitance is in farads. Okay, and a farad is equal to, well, remember, Q is equal to CV. So C is Q over V. So a farad is equal to a coulomb per volt. Is that right? Nah, that's not useful. Coulombs is in farads. Okay. Forget I said this. Don't worry about that. It's not incorrect. It's just not useful. Okay. I think that's it. Isn't that all? I think that's all we did. But you're right. I sometimes ask those questions. I often do, in fact. Okay. But knowing your forces, fields, and potentials, those basic definitions will also help with you. This is a force per charge. This is energy per charge. Right? That's why it's a joule per coulomb. Potential energy is just energy. And capacitance is something different. All right. That's all I have, unless y'all have more. Any more questions? Anything else? Y'all feel ready? Feel ready?
Maybe a weekend will help.
Okay. It's not an easy exam, but we've done everything over and over, so we've had lots of practice on it. I would love to have a good showing on it. I expect a good showing.
So what do you have to bring with this?
You bring a calculator and a pencil. You can use a pen too, but I prefer a pencil so you can erase the bubbles. Or use the same bubble form that we used for the quiz. You'll need your N number then if you don't know it. Okay? I'll be there early. I'll try to get there early too so you can get a good seat. That's all?